All right, our next presentation comes from Weiguang Cui from the University of Madrid.
Okay, great. Hello, everyone. I would like to first thank the organizers allow me to present some scientific works here. And I see that a lot of diversities that are coming from the infrastructure to the method to the technology, and this is the end part where we learn from that and what we want to know about the universe. So I would like to also say that this work is under the name of HPC and AI, and that is what I want to show you, that how we can use those to improve our learning about the universe. Let me see, it's working great. Okay, I see that a lot of people not familiar with astronomy, which is actually very old, ancient subject. And what we do, so this is the pictures we are studying. This is a galaxy cluster, this is a galaxy, and we sometimes don't have such fancy pictures. And this is the X-ray image of galaxy cluster. This is the radio image of it. And sometimes it's looking very boring. So this is the asset observing of the same galaxy cluster. So, so that is actually not all the astronomers doing that, but this is a core, this is the heart of astronomy study, because this is what we see. And that is a different story what we have seen from today, talking about the problems in the real world, that is doing medical, doing other kind of studies. In astronomy, we are actually tracing back the time. It's not looking into the future, but looking backwards. So there's a lot of other people doing theoretical study, doing simulations, and that's one part of my job as here as well. So what the problem we are at? So we are looking at galaxies, looking at different type of gas. This is gas density, and then looking at the temperature of the gas, looking at the metallicity, all those kind of things. We want to do is to understand what the underlying material. And that I bet you heard about, this is called dark matter. Oh, it's a miserable matter that which we don't know, but we hope we can know through those photons coming through those galaxies, coming through those bionts. So that is a task. So I don't put any equations here. I don't want to frighten you out. So this is the theory and the background that we would like to understand. So let's go to see that how, as I said, how we can use machine learning using the modern techniques to help us to understand that, right? We are looking at the very simple CNN model, which is just a picture, and we want to know whether it's a dog or it's not a dog. It's the same thing actually at here for astronomy. We are looking at the picture, and we want to measure it instead of, oh, yes, a galaxy or not, but we want to measure is the total mass underlying behind this picture we see. So that is quite simple, right? We just apply it. But the problem that I listed here that we are facing is that we are limited by number of samples. You know AI, you know about how this important, the sample that you have to give it so they can learn from those details. And the other thing is that also different from the real universe problem is that in theory or in observation, we don't know the real answer behind that. So that is come to the question that how we can use it. Like CNN, the answer is that we do simulations, and these two problems can be solved, let's say. So for people who don't know what simulation is, in astronomy, we do simulation is just very simply, naively assume that the universe starting from a patch of the sky with the materials random distribute only under the gravity, and also people who later on added the hydrodynamics to model the barons, all those kind of things, and evolve them to the current day, how the universe looks like. And what we see, those bumps here, there is some dark matter halo, which is hosted the galaxy cluster inside. And to be visualize it, I think this is a fantastic movie credit from the TNG simulation project. And what you are looking at right now, the top left is the density overall. And sorry, this is the gas density. This is dark matter density. And you're looking at here is the stars, how the evolving from the very smooth distribution and the gravity and the baryon physics. We model it and how they feedback. You can see it clearly from the gas temperature. And this is gas velocity, I think. And this is the sorry, this is gas velocity. This is gas metallicity. So all those things that we put together and thanks to the Dirac HPC Center, and so we can run those simulations and to see how the simulated world is evolving from the very beginning to what we have right now. So, okay, I think that is a simulation, and what we want to do is using the simulation data and try to verify that whether CN is applicable to our problem, right? So a lot of people doing the similar things try to measure, generate from the simulation. We can generate we call mock images and basically try to mimic the galaxy, how they look like, and the gas, how they distribute, things like that through the mock images from the CN method. And they are here using different tracers basically and try to recover from the image to the mass. And please note that this is only one mass, which is the enclosed the circular region of this cluster. And with this, you can see, the simulation gave us the image and the CN predicted, because we know exactly what the total mass within this radii, right? Because the simulation is there, everything is known. So this is showing you the relative difference between the predict CN mass versus the real true mass. And you can see we normally call this a bias, but you can just view it as a relative difference, and generally different methods give you the good agreement. So, okay, so the trail, I would say, look like a trail that we are walking. And how about we apply it directly to the observation? Here comes the problem that the first problem I would like to mention it before is that this simulated image, what we see is very clean, like here. But the real image is at here. The telescope observed the galaxy cluster is with not the signal, but with noise, with a lot of instrument effect, etc. So the first thing you want to do is trying to use the clean image and to predict this, it won't work. So we do a second step to add the similar systematic noise to the clean map and then do the training. And so with that, we can apply it to the real observed Planck images and to make a prediction of how the real cluster mass is. So that is the relative difference between the predict mass and the true mass, again as a function of the predict mass here. But this is only uses the clean data, which you can see that is quite good, but with slightly scatter around it. And when you add the noise into the maps, and the scatter gets increased. Okay, and that is still like we verifying this method is working. especially with the mock data, we know the true mass. But the real observed cluster image, they don't give you the mass, the real mass. And we only have predict mass from different methods. So this is the comparison between the same predict mass and the mass predicted by Planck using a different technology or different method. So you would immediately see that for the real image, we would like to see something better agreement, but it's not. And its scatter is more or less similar. The horizontal right dashed line is 0.2 difference, but there is a medium difference like around a few percent. So we thought, okay, there may be something with all the Planck provided image. We select those very good image that's very similar to observed one, very similar to the observed image without significant difference you expect, and with a little bit higher signal to noise, but still there is a difference between the predict one with the Planck one. So what's the reason behind that? So we found that we made a especially check because the Planck one, they use the scaling relation, which is based on the another kind of simulation using the true mass or the simulated mass, and they have this predict signal from the maps, and they use this signal to mass relation to make prediction of the cluster mass. So that if we, because our simulation is different from the Planck using, so if we just naively assume our simulation data result, and this is the red line which you show that is good agreement. But if we assume the black dash with error bars is the result from Planck, and if we assume their scaling relation, and you see that the agreement comes to agreement. So there comes to the second question. I think it's always facing when you're using, or even in different research field, when you're using machine learning, that is always relying on the model you provided or the sample provided. So that is something that I'm going to answer later on from my perspective. So that I forgot to mention before that as I said, the core of the astronomy is that those observed images, all information is encoded in there. Whatever model that should be reproduced it, and with all the information, and you want to not just use one quantity, right? They give you this image, you want to use as much information from it as possible. So we look like going to further is trying to understand if we can predict, instead of just one mass, we can predict the mass as different apertures, and then you can have a profile look like that. So we can still do the same one, but since the technology, the model was machine learning and AI is evolving, it's much convenient instead of for each aperture that you predict one model to do it. And you can do is using this autoencoder, which is subtract the most important features from the image, and you do a regression with the random forest. Very easy that you can immediately have the dark matter density profile, the gas density profile, and all the way out to the image. And the more important, here I show the relative mass difference again as a function of our density, but you can treat it as a radii. So I would say very important another method is that it's not because there is no relative difference, but also look at the scatter. It's shrinked. It shrinked from 1 point or 0.2 to almost 1. And with this, and we can even do more things because we have know the profile, and we can do the quantity of this profile, which is normally quantified by this called concentration parameter. And from that, if we apply to the real image, we not only know the profile, but also know how well it can be described by the NFW, the well-known halo profile. And that is showing the prediction difference with respect to the real difference. So, okay, and this is like say that from one data point or 0 point to 1D profile. And still, we can do even more, which is that not only about 1D profile, we can even do the 2D maps. And that is relying on also evolving a newer and more advanced machine learning model. And right now, we have it input from the different observations as that X-ray, which is tracing gas, basically gas distribution, and we also have stars, and with that, we combine them together and trying to predict what the underlying dark matter or total matter density field look like. And so that is the result we are trying to use. This is called the UNet. I'm going to show you again later on, but let me show you let me explain to you a little bit about here that this is the predict 2D maps with one single feature as input for the stars. And if you combine them, and you can see that the two maps are extremely similar. And I will show you that later again how fantastic this method is. And this is the residue for the maps. And you would see from the top and to the bottom that the residue is gradually reduced. So the UNet, assume that some of you maybe know a little bit about this, and just very simply that you can treat it like decreasing features and subtract the most important and upper folding it again with the skip connections between them. And with that, you can train the maps from the different input. You can specify like only use one image, or you can use multiple image to make predictions of the total maps. So let's see the image. It looks very similar, but quantifying it is not that easy, I would say. So we do first, of course, is trying to do the density profile. Again, try to see the relative difference between the predict total mass and the real mass. And this is really right now we can calculate in R200, which is just a particular radii where the image covers. So instead we fix into several points as in previous autoencoder method. Right now we can just try to as many points as you want. So, and another amazing thing, like I said, is that also the individual input give you a little bit larger scatter, which is compatible to the first CNN method. But if you go to the combined one, you can have a look at the scatter. It's reduced to only a few percent. So that is really amazing that if we can later on apply this method and to replace the weak lensing method, and which is has been proposed by using by Euclid to mapping our universe, the matter distribution, or to high redshift, etc. And this is, I would view it like a future that we can provide even more better result. But okay, let's go a little bit more details about quantifying the difference. The other way is trying to see the power spectrum, and this is as function of radii again that you see the different features, different input, single input, showing that the small scale, which is a little bit deviated, but if you combine them, it's getting better and the error is reduced. And this is another method to quantify the relative difference between the maps, and which is commonly adopted in very fast. So commonly adopted in the machine learning community is called maximum mean disparity, which is basically calculating that predict value with the real value for each pixel. So this is showing also very good when you do the combining method. The other thing that I said that this is more or less from the observational side to understand the background. But we can reverse it in the same way is that from the underlying background of the matter, dark matter, and we can predict how the current observation image should be. So that is a reverse method did by a student me and trying to understand that whether we can use this total matter density maps and to predict what observers the maps look like, and it's very similar again. So that is very useful because this one that allow us to, instead of running the simulation again with all those bio models, because which is very, very time consuming and the computation cost very high, and we can simply apply those techniques to the dark matter only simulation, which is fast and easy to manage and to make predictions how this observational images look like from those dark matter only simulations. So back to the last second question, I would like to explain a little bit more how I would like to overcome this problem that always we do the simulation, we provide the sample, and all your method, all your result is relying on it. What if your model doesn't give you the correct answer and you are making wrong predictions, right? So I think the way is slightly different. Viewing it is that we use machine learning as a method, not as explanation. So that is the way how we can overcome it. If we use it as a method, and either you very simple example that you use your finger count to calculate 1 + 1, or you use a calculator, or you use your laptop. It's just a tool, and it gives you answer, and the answer can be verified. And if it doesn't matter which tool you use, right? So this is come to the question that solution is that we only use the machine learning as a tool to make the correct get the correct answer, but the explanation is back to the simulation, which we adopt the simulation parameters and everything, try to reproduce the exactly the same answer that we see in the universe. That is a tool, right? Only with that we can use the simulation to explain that how it's really forming and whether this model, what we expect from this model. So that is the explanation which is giving to the machine learning giving to the simulation, while the giving to the model or simulation, while the machine learning is only play a role in as a tool. So this is the future. I would say that how we can overcome this second problem. So this is an image, and I know that a lot of people not astronomers, so this is a question. This is image of the coma cluster. So which one do you think is the real one? The upper one or the lower one? Yeah. Okay, the upper one is the real cluster, the real coma cluster, and the lower one is the one we simulate based on a constrained initial condition that we can try to reproduce more or less. It's not exactly the same as the real one right now, but with those techniques evolving, and we expect to predict exactly like that. And with that, that's what I mean. The machine learning is using as a tool. With that, and we can use simulations to explain what we see, what we understand, etc. So, okay, so that is my future aim, and for that, I'm done. Okay, and that is conclusions. So I would say that machine learning is a very, very powerful tool, and we can use it, and it help us a lot. And the future is there, and it's also bring a lot of interesting results. We can try to understand with that, but we have to use it wisely and carefully. And we have to know that what is behind that. It's not exactly to know behind that. If you use it like a tool, and you probably won't need to know that what really inside the black box. But we have to be aware of that what we get is relying on the input of the sample. Okay, so yes, that is the result I would like to share with you, and hopefully that with both the computation power and both the infrastructure we have and also the advanced technology, we can go to even further to make more interesting and fantastic scientific results. Thank you.
Thank you, Weiguang. You know, I'm interested in terms of the picture. Why? Because I'm a novice or don't know myself. What made you go for the upper picture? What was? There was an artifact. Okay, all right. I was looking for something. Where?
Yeah.
Is it because of the light? Yeah. Okay.
Yeah.
So I was thinking that might be it, but I was like, oh, maybe that's some special layout or something there. That's how stars should look. Anyone have any questions?
What sort of computation power does it take to allow the bottom one to match the top one?
It's very cheap, I would say. This one is just try to forecast on the coma cluster. It's a zoom-in simulation, so you don't need too much computation power. I think it's like maximum a few million CPU hours. Yeah. So, but of course, that is depending on how large scale your simulation will be, right? And this is very small region. But if you want to go to cosmological one that want to resolve many things, etc., and that really costs a lot. So that is will be relying on the future development of the Dirac. Yeah. Thanks.
Any other questions? Okay, thank you very much.
Thank you.